Good morning, everybody. This is Dr. Momin. I am going to give you a medium presentation in here on the set theory, which is part of chapter 1. Our chapter 1 of our textbook is called Fundamentals. The first topic of the fundamentals would be the set theory. We'll introduce a set and we will use that set in different chapters. So let's start with the definition of a set. A set is a structure representing an unordered collections of zero or more different objects. So for instance, you can have a set of the names of the students in the classroom. And so since they are all different names, then that will be the set of names in the classroom. We start with some notation for the sets. We use the upper letter S, T, U, capital A, capital B, and also on. We use the notation also capital U for the universal set, as we will introduce it later on. We can denote a set S in writing by two ways. One way of listing the individual items in the set. So if we have a set, for instance, that has the three letters lowercase a, lowercase b, lowercase c, then we have to put it into this definition listing procedure, which we open curly parentheses and we put A separated from B by a comma, and then another comma, and then C, and then we close the curly parentheses. We only use the curly parentheses in that idea of a set, and we also use it in the next definition as also a curly parentheses. A round parentheses is not referred to a set. A round parentheses could be used for an interval, could be used for an element within the set, as I will introduce it later on. The second definition, or the second way of identifying a set, is called the set builder notation. So what we have here, we have a condition on the defining the set. So for instance, the definition, what is the set of the numbers that are between 0 and 5, not including 0 and 5? So we put it this way. We open a curly parentheses, we say x, and we always use x as a variable indicating these possible values. And then we put this line in here, which is called such that. So we read it x such that. X is an integer, because we wanted an integer between 0 and 5, not including 0, not including 5. So that is the second way of identifying the set. Now, the order doesn't matter in a set. So if you have the three distinct or different values, A, B, and C, you can put them in any order, and they represent the same set. Now, you can also have some sets where the letter is repeated, but it is actually has only three different letters, little a, little b, little c. And so those two sets in here are identical. Now, so two sets are the same if they have the same objects or the same items with them as them. Here is a definition of a set that has the numbers 1, 2, 3, and 4. And so you can put it as a list way, that what we have in here, 1, 2, 3, 4, separated by commas, and starting and closing with the curly parentheses. Or you can put it into the set builder way, where you say x such that x is an integer between 0 and 5. Or you can put some conditions also, such as that you're ending up with the same values, integer values, 0, between 0 and 5, not including 0 and 5. So If they are integer values between 0 and 5, then they are the same as if you square them, they will be between 0 and 25, not including 0, not including 25. Now, I will introduce in here some common notations for very important sets that we will use it throughout the book. I will introduce them in here and then I'll add some more. The first set is called the natural numbers, and the natural numbers are the integers starting with a 0. So it is 0 or positive integers, 0, 1, 2, 3, and so on. Versus the set of integers which have the possible negative integers, the 0, and the positive integers. Another set in here which is called the real numbers are, and it could be any number between 0 and infinity, or negative numbers also, but it has the possibility of having a decimal point. But we will distinguish later on between two sets that are a subset of R. One is called the rational numbers and the other one is called the irrational numbers. The rational numbers would be, we call it Q, and it is identifying a rational number Q is identified such that it is represented as a ratio of two integers. Let's introduce them in here in this some more subsets in here of, or some more notations for sets. The Z, as we introduced it, is a set of integers, positive or negative or 0. The N, which is the non-negative integers or 0. The Z plus, which is the set of positive integers. We can also identify Z minus as the set of negative integers. Q is the set of rational numbers. So any rational number can be represented as an A over B, where A and B are both of them are integers. But B cannot be a 0. You cannot divide by a 0 to identify rational numbers. So for instance, a rational number can be 5, which is represented as 5 over 1. Could be 2.5, which is 5 divided by a 2. And then we have the Q plus, which is the set of positive rational numbers. And then we have the set of real numbers, and the set of real numbers, as I identified before, is all the numbers between minus infinity and infinity, decimal or non-decimal, integer or non-integers, and so on. And then we identify the C, which is the set of complex numbers. We will not be using the complex numbers in our discussion in the course. So we can see that into the solution of equations, where the solution includes a square root of a negative number. Here is another thing here about the comparison between a set and an interval. All right, when we wanted an interval on the real line, we can identify an interval that includes the endpoints. So if we are looking into a straight line and we wanted to have an interval between A and B, including A and B, we call it is a set of x's, where x is a real number, but x is between A and B inclusive. And so we use both sides in here, we use the square parentheses versus the round parentheses that doesn't have A and B, or the mixed ones where it is closed from the bottom and open from the top, or the other way around. Now, I will introduce in here the some operations on the sets. One of them is called the union of the two sets, and the union of the two sets I will represent it in here, and we will see it throughout also the what we call the Venn diagram. It has the elements that belonging to A or to B or to both, versus the intersection that has the elements that are common in A and common in B. So it is common to A and common to B. So it is a smaller subset for the intersection than the union. Now, We will see that on the Venn diagram. We can see it also some examples as we will see later on. And then we talk about the difference between B minus A. So B minus A will be the elements that are in B but not in A. So we take the elements that are in B, and if they are mentioned in A, we subtract them, we remove them, and so we will have the difference. Here is the Venn diagram idea. Venn is a mathematician from France, a French mathematician who introduced these ideas about representing the union, intersection, and the complements and so on into a diagram. And using that, it helps a lot to solve a lot of problems that we see it in mathematics and computer science. The basic relationship in here is that we say we use the first some notations in here. We refer to the element within the set as little x, and we use this notation as belonging to. This little a in here is an element of S, or x belonging to S. So x is an S, is an element of the set. Now we notice later on the difference between an element belonging to a set and another set which is a subset of another set. That is a different notations. So we define in here an element that belonging to this one in here. The empty set. The empty set is a set that doesn't have any elements. We call it the empty set, phi. The notation in here, phi. And we also refer it to as an open parenthesis, close parenthesis in here, but no items. Now remember, there is no item in here, but the notation is called phi, or like this. And this happens when you're trying to put it into a set builder, but the condition is a false condition. For instance, the condition could be x such that x squared equal to a minus 1. There is no such x that if you square it you get minus 1. So it is an empty set. Or x squared plus 25 equal to a 0. X squared plus 25 is the same, equal to a 0 is the same as an x squared equal to a minus 25. Therefore, you cannot have an x equal to x squared equal to minus 25. There is no such x. Now, we talk here about a different notation in here, which is a subset. S is a subset of S if S has some elements that belonging to a T. So it means that every element of S is also an element of T. So we refer to it like this, and we use S as a subset of T, such that every element X that belonging to S should be as belonging to a T, not the other way around. As an example, S will be the set of pregnant women, and T is the set of women. Of course, pregnant women will be a subset of women, and so here is an example that referring to this relationship. If S is not a subset of T, we use this notation in here that S is not a subset of T. In terms of the Venn diagram, then we will have the T in here as the bigger subset, the bigger set, and S is the smaller set that belonging to, or excuse me, that is a subset of T. As an example in here, S has elements 1 and 2, T has element 1 and 2 and 3. Now remember also S can be equal to a T. So S could be 1, 2, and 3, and T can be 1, 2, and 3. So one set will be equal to the other one, and we refer also in that case that S is a subset of T, and T is a subset of S if they are equal to each other. Here is some notations in here for what we call it the the possible subsets of a set. So we have a set that has the elements 1, 2, and 3. Using the power notation, we're using the set builder notation. It is the set S such that x is belonging to the numbers 1, 2, and 3, or x is between 1 and 2, 1 and 3 inclusive. So what are the possible subsets of S? Well, the first one is 5, and you put it into that. And another set would be 1. Another subset will be a 2. Another subset will be a 3. Another subset will be 1 and 2, 1 and 3, 2 and 3, 1, 2, and 3. How many do we get? We get 8. And the reason for this is that we have 3 elements in the set S. So the number of possible subsets will be always including the set itself, 1, 2, and 3, the 5, and another subsets in here that has the individual ones or the 2s, and so on. And the number will be always equal to 2 to the power of how many elements in the original set. So it will be 2 to, in our case in here, 2 to the power 3 will be 8. If we have a set that has 5 elements, like A, B, C, D, E, then the possible subsets will be, the number of possible subsets will be 2 to the power 5, which is 32 possible subsets. Now, this ordered in the tables in here introduce us to something that we will be using in chapter 4, which is the relationships and functions. And it is also used a lot when you're doing algebra and you are working with the domain of x and y. So here we're talking about the Cartesian product. Imagine that you're doing a graph for a function, and x is the domain and y is the range. The same thing in here. We have 2 sets. One set has A and B, another set has 1 and 2. So if we're looking at the Cartesian product of the first set, let's call it A, which has A and B, and the second set B that has the numbers 1 and 2, if we do the Cartesian product A times B, then we will take the first element belonging to the first set and second element belonging to the second set, and we do all the possible values in here from A and B. Alright, you can extend this one to a multiplication, a cross product, or a Cartesian product of more than 2. So you can say A times B times C if you have 3 sets A, B, and C, and so on. And then it will have triples. The items will be triples. Like the first item in each element will be from the first set, the second element will be from the second set, and the third element will be from the third set. Alright, now the union in here that I referred to before is the elements that belonging to either x, or x belonging to A, or x belonging to a B. So here is an example. Suppose we have the set have letters A, B, and C, and the second set has numbers 2 and 3. So the union will here, because those 2 sets have different items, all we have to do is just to list all of them in there. So it will be A, B, C, and 2 and 3. Now, if we have 2 sets that are similar, but one of them has different items, and then also they have also common items. So what we can do in here is we will take the elements that are in the first set, and the element in the second set, and the element in the common. So we, in this case in here, we don't repeat the common elements. So we will have 2, 3, 5, and 7. So remember now, 5 was repeated, we removed this one, and 3 was removed once. So we ending up with the diagram in here. The number 2 is in the set, first set, that doesn't belong to the second set, and the 7 is in the second set, doesn't belong to the first one. 3 and 5 belong to the what we call it the that part in here, we call it the intersection. The whole thing in here is called the union. Now, if we refer to the intersection, then the intersection would be the common elements between A and B. So here is an example. Two sets that are not intersecting, we will have their intersections have an empty set because they don't have a common elements. So the set in here that belong to the intersections or that has elements between the first set and second set will be an empty set. Versus this one in here, the first set has 2, 4, and 6, and the second set has 3, 4, and 5. 4 is the common element. So the intersection in here will be a set, still a set, and use the notation of the set, and it has the number 4. We call two sets that don't have any common elements, we call them disjoint sets. So like the examples that we have over here, this set in here and this set in here are disjoint. They don't have any common elements. So their intersection will be an empty set. Versus these two sets in here are called joint sets. So they either disjoint, two sets are either disjoint or joint. Sometimes we call them also the disjoint, we call them mutually exclusive sets. All right. We refer also to the differences that I mentioned before. A minus B now the set difference in here, as I identified before, if we say A minus B, then we keep the items in A, we remove the items from A that belong to a B. As we can see from this next graph, we have a set that has the numbers 1, 2, 3, 4, 5, and 6, minus another set that has some common elements, which is the 2, 3, and 5. So the resulting difference in here will be the original set minus the elements that were mentioned in the second set minus the elements in B. So A minus B will have 1, 4, and 6. Another example in here, if we're looking at the Z, which has all the integers, minus the natural numbers, which are the 0, 1, 2, and 3, and so on, then what we would be left on in here will be the set of Z minus, which are the negative integers. Alright, now here is another example of the Venn diagram for that difference. A minus B will be that red part in here, which is we removed the common part between A and B, we removed it from this. So the difference in here will be A minus B. As we will introduce later on, we can have also the symmetric difference. We can have A minus B and B minus A, which is this part in here. That blue part, that light blue part is called the B minus A. And this red part in here is called A minus B. And that part in here is the intersection. Alright. The complement, by definition, we define a universal set. For instance, if I'm talking about a classroom, and the classroom has students that are male and female, and if I have the set A of the names of the females, then the complement of this one will be the names of the male students in the classroom, which will be the rest of the classroom not included in A. So here is a set of examples, an example in here of a set 1, 2, 4, 6, and 7, and so on. If we look at the natural numbers 0, 1, 2, 3, and so on, and we take off from this the set A that has 3 and 5, then the complement of 3 and 5 would be 0, 1, 2, 4, 6, and so on. So it is the rest of the natural numbers that are not in A. Here is an example on the Venn diagram. Here is the set A. The blue part in here would be called the A complement. So this is A complement. of course, the union of A with A complement would be the universal set U. The whole box would be A union A complement. Here are some identities that are very important in our discussions. The union of A with a phi is equal to an A. Now remember, this is the union, and the phi is an empty set. So you don't add anything to A actually by taking the union with phi. So, but the intersection of A with the universal set, since A is part of U, then the intersection of a set which is with the bigger set that contains A, which is the universal set, will be equal to an A. Now the domination A union U is equal to a U. A intersection with phi is equal to a phi. Now remember, there is no common elements between phi and A, so it is still no common elements, which is the phi. A union A is equal to an A, and A intersection A is equal to an A. The double complement, the intersection, the complement of the complement is back to A. The commutative property is A union B is the same as B union A. A intersection B is the same as intersection B with A. That applies also to more than two sets. And we can use in that case the associative property in this case. Now, this is a very important one. We use it in here. We use it also in the logic when we talk about the negation in the logic identities. The De Morgan theorem, De Morgan again is one of the mathematicians that has looked at this. And what we have in here, we read it this way from left to right. We read it as it is the complement of the union is equivalent to the intersection of the complements. So we read it this way. It is two sets, A and B. We form the union, and then we take the complement of this. The complement will be the rest of the universal set that is not in the union of A and B, which is equivalent to the intersection of the complement of A and the complement of B. The other identity in here, which is the complement of the intersection, is equivalent to the union of the complement. So we have to reverse it this way. Now we have this thing in here about a combination of intersection and union. This is similar to when you're doing a multiplication in mathematics. You have A intersect with, and then parentheses, the union of B and C. So the left hand side says A intersect with B union C. The right hand side would be A intersect with B union A intersect with a C. So if you have, for instance, in here in multiplication, you have 5 times 2 plus 6. It is the same as 5 times 2 plus 5 times 6. Now that is what we are looking at in here. We can also look into the other way around, which is A union and then B intersection with C. Now let's move to the more on the union and intersection, and how do we use it in some examples. However, we have covered some more identities in our book. I'm going to refer to them in here, and we will continue with some examples. The first thing in here, the double complement. This is a double complement in here. A complement of complement is equal to an A. The De Morgan theorem that we see, the commutative law, the associative law, and this one in here that I was talking about last is the distributive law or the distributive rule. it says A union B intersection with a C is equal to A union B intersect with A union C. The other one in here that I started with before, which is like the multiplication, it is A intersect with B union C is the same as A intersects with B union A intersection with C. Some other laws that I referred to before. Now here is a diagram that shows the complement and the intersection, and the union would be the whole two circles together. But the intersection in here is this shaded area. An example of how do we use this one. Now, let's refer first to the cardinality, which is how many elements in a set. So we refer to the cardinality as how many elements in the set. What we refer to as the number of elements would be how many elements, and we use counting. So for instance, the set A here has 30 elements. The set B in here has 25 elements. So the number of elements in A, as we see in this example in here, we looked at 50 students. 30 of them are studying the language basic, 25 studying the language Pascal, and 10 studying both. So here when we do the counting is how many in A, we refer to this lines around A, we call it the cardinal of A, and then the cardinal of B, and then the cardinal of the intersection. So we have a rule in here says that the cardinal of the union, how many elements in the union, is equal to how many in the first set plus how many in the second set minus how many in the intersection. So in this example, when we draw the diagram, we have to start with the intersection first. We put the intersection in here, which is 10. And then we subtract 10 from 30. We get the second part in here, which is the 20 that are in A but not in B. And then we go to the other part in here. We have 25 all in B. So in order to identify this part in here only, we subtract 10 from 25, we got 15. So now the union has 20 plus 10 plus 15 has equal to 45, which we can also get from here by taking 30 plus 25 minus 10 equal to 45. Now remember, now the rest of the group, which is the 50 students, will be outside in here, which is the 5, which is the complement of the union. This is the union, this is the complement of the union. We can look at it, this one in here, as it is the intersection. That 5 is actually the intersection of the complement of A and the intersection with the complement of B. And those are the 5. Here is another example where we have 3 sets, A, B, and C. And this example is going to help you with do some of the problems in section 1.2. What we have in here, we have 100 samples that has possibilities of 3 types of defectives. You can have a defect to only some items has only one defect, either A or B or C. Some elements or some samples has 2 defectives, A and B, or A and C, or B and C. Some samples has the 3 defectives. So we identified in here that we have 23 samples that has defective A. It could be A by itself, it could be A with B, it could be A with B and C. And then we have 26 samples that have defectives of type B. The same thing with the C. We have 7 samples that have defective A and B, 8 with A and C, 10 with B and C, and then 3 has the 3 defectives A, B, and C. Of course, there are some samples also could be have no defectives at all. And the question in here, can you draw the diagram, the Venn diagram, and can you identify these items in there? And after that, can you answer these questions? how many have defectives, which is the union of A, union B, union C. So it is the union A, union, it is the set A union B union C. Or how many don't have defectives, or how many have exactly 2 defectives, or how many exactly has 1 defect, or how many have 3 defectives. Of course, the 3 defectives are given in the answer in the problem itself, which is these 3 samples has A, B, and C. So let's look at the answer and how we construct that Venn diagram. We start with the diagram by putting 3 sets intersecting in here. This is A, this is B, and this is C. So we've put them in with no numbers yet. And then we start with the smallest information, the number for the smallest part in here, which is the intersection. And how many elements in A intersection B intersection C is the 3. And so we identify that 3. Now to fill in the other numbers, we look into what do we have in here. This is set A, this is set B. The information given to us is that A intersect with B means that there are 2 sets that has possibilities of common elements, which is A intersection B. But we were given that information that 7 items has defectives A and B. So in order to identify that, we subtract 3 from 7 and we get 4 in here. So those 4 actually have exactly A and B, not C. All right. Now we come over here and say, well, do the same thing in here. Between A and C, we were given that 8 items have A and C. They said they have A and C. But now we get this 5 by subtracting 8 minus 3. We do the same thing between B and C. We were given 10 items. We put 3 in here. 3 from 10 equal to a 7. Now, so that is the diagram. After we get this, then we start filling in this part in here, which is what is in A, only A. And so we originally were given that we had 23 in A. So in what we do now, we get from the 23, we subtract this 4, we subtract 3, and we subtract 5. Those are 12. 12 from 23 gives me 11 in here. We go to a B. B was given that we have 26. If we subtract these 3 numbers, we get 12 in here that are only in B, not in C, not in A, only in B. Only 1 defect, which is type A. The same thing with the third set, those 15 coming from the 30 items minus these 3 numbers, 3, 7, and 5. After we identify this one in here, then the union now will be the sum of 11 plus 4 plus 12 plus 3 plus 5 plus 7 plus 15. Or we could use this identity about the cardinality of the union of 3 sets. The cardinality means the number of elements in the union is equal to the number of elements in A plus the number of elements in B plus the number of elements in C minus the number in the intersection of A and B, and also the minus also A intersect with C minus B intersect with C, and then we add the intersection of A, B, and C. So we can calculate it from this way without the Venn diagram by looking and say, well, we can put 23 over here, we can put 26 over here, we can put 30 over here, and then we can subtract the 8 and the other numbers 7 and so on. And then we add the 3, and that will give me also the 57. As I can see in here, 23 plus 26 plus 30 minus the intersection 7 and the 8 and the 10, and then we add the 3, we get 57. However, the Venn diagram helps us to answer the other questions. How many samples exactly 2 defects, but not identifying which ones. So we have 4 in here that has A and B, exactly A and B, 2. We have 5 in here that has exactly A and C. and then we have 7 items in here that has exactly 2, which are B and C. So the answer to the question in here for that will be in how many has exactly this will be 4 plus 7 plus 5, or 4 plus 5 plus 7. These are how many samples that has exactly 2 defectives. And then if you wanted how many samples exactly has 1 defect, then that will be 11 plus 12 plus 15. How many have exactly 3? Those are the 3 items. How many don't have any defectives at all is 43. If you add all of these numbers, then you get 100. I will refer to also each one of those as we identified as part 1, part 2, and so on. And we get these parts by doing the subtraction that I mentioned in here. So look at that in the PowerPoint presentation that also is given on Moodle. I would like to advise you to use that PowerPoint that is in week 1. Read this thing in here, review this video twice, listen to me, and do me a favor by going into the odd number problems on the relevant sections and do them. After you read the examples in the textbook, go and try yourself, give yourself the confidence by doing the odd numbers, and try to compare your odd numbers to the answers given at the end of the book. If you have any differences between your answer and the answer given in the book, assume that the answer given in the book is correct. So check your answers and see maybe you made a silly mistake. If you cannot figure out why, let me know, email me or send me a message, and I can try to explain to you. Good luck to you guys, and have fun with the course. I will do other presentations for the different topics in the different weeks. Good luck to you, and good luck with the first week assignments.